Welcome! Today we'll explore coordinate systems and curvilinear coordinates. Let's start with the basic transformations between different coordinate systems. Let's begin with the transformation from Cartesian to polar coordinates in 2 dimensions. Here we have our familiar xy plane. For any point P, we can describe its location using either x and y coordinates or using r and theta in polar coordinates. The transformation formulas from Cartesian to polar coordinates are x equals our cosine theta, and y equals our sine theta. The inverse transformations are r equals the square root of x squared plus y squared, and theta equals arctangent of y over x. Now, let's move to 3 dimensions and look at cylindrical coordinates. Cylindrical coordinates are like polar coordinates extended into 3D, where we keep r and theta from polar coordinates and add a z coordinate that works just like in Cartesian coordinates. The transformation formulas for cylindrical coordinates are similar to polar, but we keep z unchanged. X equals our cosine theta, y equals our sine theta, and z equals z. Finally, let's look at spherical coordinates. In spherical coordinates, we use r for the distance from the origin, phi for the angle from the z-axis, and theta for the angle in the xy plane. The transformation formulas for spherical coordinates are x equals our sine phi cosine theta, y equals our sine phi sine theta, and z equals our cosine phi. An important concept in all coordinate systems is the differential volume element. In Cartesian coordinates, it's simply dx dy dozen. In cylindrical coordinates, it becomes our dr d theta dozen. And in spherical coordinates, it's our squared sine phi dr d phi d theta. Finally, for general curvilinear coordinates, we need to consider the metric tensor and Christoffel symbols. The metric tensor describes how distances are measured in our coordinate system, and the Christoffel symbols tell us how vectors change as we move along curved coordinate lines. Understanding these coordinate systems and their transformations is crucial for solving problems in physics and engineering, especially in fields like electromagnetism and general relativity.